So, dear professors, today I'm going to talk about the exact exponential algorithms and the parameterized algorithms. And I will, to talk about the exact exponential algorithm, I will use the traveling salesman problem by dynamic programming to do the presentation. And for the other part, parameterized, I will use the bar fight prevention to make the illustration. And yeah, let's talk about the traveling salesman problem via dynamic programming. We can divide the whole problem into two parts. It would be the addition to the tour of the minimal length from C1 to Ci, and the other term is that the distance from Ci to C1. Then, so basically we have OPT SCI. This actually stores all the minimum length, the tour of the minimal length from C1 to Ci. And so the first step is that we calculate all the distances from C1 to Ci and put it onto the OPT SCI, and then we keep enlarging the size of the city set, and we calculate the tour of the minimal length from C1 to Ci if the city set S is more than one cities. And we use the equation here, OPT S minus subset minus Ci and the CK and plus the distance of the CK to Ci, and the CK should from S subset minus Ci. Yeah, here, so we can get the lemma here. The lemma is actually the calculation. If S equals to Ci, that means the city set only contains Ci, the city, and the calculation will be distance over there. And if the city set is more than one city, then that means if Ci is subset of S, then we calculate minimum of the OPT S minus SCI plus D CK from S. Yeah, and this is our lemma. And how do we prove it? We can assume that if our K equals to 1, then it is the first case, then we are done. And if K is not equals to 1, we will use the second case. And we just assume that we define that E is the last edge on such a path. So E equals to CK and Ci. So when K equals to 1, it will be the first case. And when K is not equals to 1, it will be the second case. And the shortest length going through E will be using this formula, and the shortest path must be use the minimum of the CK from S set. This. So here we got proven, and then we have another lemma, which is actually said the number of the shortest path is that we calculate is O of n to the power n squared to the n to the power n squared times 2 to the power of n. And how to prove it? It's actually, we can see this is from the second case, and we prove it by calculating the second case. We analyze how to prove, and because we know that we keep enlarging the cities set from 2 to n minus 1. So it would be the sum j equals to 2 and to the n minus 1. And then we notice that we overall have n minus 1 cities, and we just take j cities, take any subset of j of them. So we have n minus 1 choose j, and we also need to pick the last one every time. So we have I equals to 1 to j and j minus 1. Yeah, and we can see by our observation, we can know that this and this is actually bounded by n, and both of them are bounded by n squared. And so we get the n squared of this one, and we bring them into the front, and we can relax this part. Will be the and this is actually n choose j, and the sum of the j equals 1 and 2 n and n choose j. And this is n squared, and this is actually n squared. This times 2 to the power of n. And hence we got this number of the paths. And now we introduce a new notation of the O star. When we comparing the algorithms of the exact exponential algorithms, we ignore we don't care about the polynomial factors. And what we do is we define O star, Fn in O star equals O star of Gn is actually equals to if and only if there exists constant c in real number, and O of Gn times n to the power of c. Yeah. So this is a definition of the O star. That means the O star is actually the same as O, notation O, but it ignores the polynomial factors. So our lemma will be the number of the length is the shortest path is we calculate is actually the O star of the 2 to the power of n. Yeah. And then let's talk about the bar fight prevention algorithm. And the problem is actually we need to block at most k people to prevent there's conflict. The naive structure is that we just try all the possibilities so it will be the possibilities of the n choose 2, and we check whether there exists any conflicts here and whether k is the correct size. And but it takes a long time, so how do we address it? How do we improve it? We just because we use the fact of the at most block k people, so we we only try n choose k possibilities, but this still takes a long time. So we simplify the algorithm by using the conflict graph. How do we do that? We just for the first case, we think there is a person who have no conflicts with anyone else, so we just let him in, and the corresponding meaning in the graph is that the degree of the vertex is actually 0. So we let him in because he's very safe. There is no people will conflict with him. So yeah. And for the second people, and we just drop this vertex from our graph. And for the second case, if there is a people have conflicts with more than one k plus 1 people, that means then we need to block him, because otherwise we will block his neighbors. But at most we can only block k people, then we block our break our constraint. So we just block him, and we just remove him from the conflict graph. And what about the we can observe that if one person involves at most k conflicts, and if the number of the edges in our graph is more than k squared, then there will be no solution. That is because if we block one person, that means we can only solve k conflicts, and we can at most block k people. That means we at most prevent k squared conflicts. So yeah, so we combine these three ideas, and we can reduce our conflict graph into a subgraph that the subgraph with the size of the vertices is only 2k squared. How do we get that? Because the size of the v prime is that we at least one edge at least one edge in at least one edge here, and we just v in v and 1, and it is actually less or equal than the sum of the v in v dv, and this is actually the 2e, and this is actually 2k squared. So that means we can get a better solution right now. We can only try 2k squared and choose k possibilities. But we can still get better. That we can consider there's a person who will only fight with exactly one purple. So we can reduce this. When we think about this case, we block him or his neighbor is actually the same, and the case will not get worse. So what we do is just we can reduce our graph into a subgraph that with size of the vertices only k squared. How do we prove it? Is that because from here it is similar with a previous example, and we can get the k squared here, and then we can only try k squared choose k possibilities, and it's actually a viable solution. So that's all.